Welcome to The Explainer. Today, we're diving into something that every single Go developer runs into, the type system. You've probably asked yourself, why is Go so, strict about types? It's a great question, and in this explainer, we're not only going to answer it, but we'll show you how to master Go's type system to write way safer and cleaner code.
So let's just jump right in with that big question, because honestly, it gets right to the heart of why Go was designed the way it was. You know, if you're coming from a language like Python or JavaScript, Go can feel kind of rigid. It just flat out refuses to automatically convert an int32 to an int64 for you. But trust me, there's a really good reason for it.
And here's the key thing to get your head around. In Go, this strictness isn't a limitation, it's a feature, a huge one. It's all about making you write safer, clearer code by forcing you to be explicit. Think of it like a very picky copilot. They might annoy you by making you double-check every little thing before takeoff, but they're also the reason you don't crash and burn later.
Okay, so how do we actually work with types day to day? Let's get into the toolkit. We're going to break down the three main tools you have for manipulating types: conversion, assertion, and casting. By the end of this, you'll know exactly what each one does, when to use it, and, most importantly, which ones are safe, and which ones are, not so much.
First up is type conversion. This is your bread and butter, the tool you're going to use 99% of the time. It's your standard, totally safe way to change a value from one type to another, like turning an int into a float 64. The best part is, it's all checked at compile time. The compiler has your back. If you try to do a conversion that's not allowed, your code just won't build. Simple as that.
Now, here is a super important detail you have to remember. A conversion always creates a brand new value in memory. This isn't just trivia. It's a huge deal for performance. When you convert a big string to a slice of bytes, Go is literally allocating new memory and copying all that data over. Now imagine doing that inside a loop that runs 1,000,000 times. Yeah, that overhead can really add up, so definitely keep that in mind.
All right, let's move on to a more specialized tool, type assertion. When you have an interface, it's like a box that can hold anything. You don't know what's inside just by looking at the box. So you can't really convert the box itself. What you want to do is figure out what's inside it. An assertion is basically you saying, hey, I believe there's an integer in this box, and I want to take it out and use it.
But, and this is a big but, this tool comes with a risk. This is a runtime check, not a compile time one. If you're wrong, if you assert that an interface holds a string when it really holds an integer, your program will panic. It will crash hard. It's like reaching into that box, expecting a cute kitten, and pulling out a snake. It's a nasty surprise you want to avoid in your production code.
So what's the pro move? How do you do this safely? You use the "OK" idiom. This is the standard, safe way to do a type assertion in Go. It's like peeking in the box first. You get back two values, the value you wanted and a Boolean that's true if you were right and false if you were wrong. No more panics. You just check if OK is true and handle things gracefully if it's not.
And finally, we have typecasting. Now, listen up, because people sometimes use casting and conversion interchangeably, but in Go, they are worlds apart. Casting is the dangerous power tool in the back of the shed. It's tied to low-level, unsafe pointer operations, and it's something you should almost never touch in your normal day-to-day Go code. It's powerful, but man, is it easy to hurt yourself.
Just look at this code. This completely bypasses Go's safety net. It's you telling the compiler, hey, forget everything you know about types. Just treat this chunk of memory right here as if it's a pointer to a float 64. It's powerful stuff for things like C interoperability or squeezing out every last drop of performance, but it is incredibly dangerous. One wrong move and you're dealing with corrupted memory and all kinds of weird bugs.
All right, let's switch gears. We've talked about changing types. Now let's talk about creating new names for them. Go gives you two ways to do this, and I'm not kidding, understanding the difference is a huge deal. This is one of those things that really separates the beginners from the pros.
Okay, look closely here. On the left, we have a type alias. On the right, a defined type. What's the difference? It's just an equal sign. That's it. One single character. It's kind of amazing how much of a difference that one little symbol makes. Let's dig into what it actually means.
So a type alias, the one with the equal sign, is just a nickname. That's the best way to think about it. You're not creating anything new. NewName and ExistingType are 100% identical and interchangeable. The compiler sees them as the exact same thing. You can use them in place of each other anywhere, no problem.
So why would you even do this? Well, the number one use case is large-scale refactoring.
Imagine you have a type called user that's used in 100 different files, and you decide, you know what? A better name is customer. Instead of a massive, risky find and replace, you can just create a type alias. This lets your old code and your new code live together peacefully, so you can migrate everything over gradually. It's a lifesaver.
Now, a defined type, the one without the equal sign, is totally different. This creates a brand new, distinct type. It's not a nickname. Think of it like you made a photocopy of a document and gave it a new title. The contents might look the same, but it's officially a separate thing. They are not the same type, and you can't use them interchangeably without an explicit conversion. And this is where things get really powerful for building solid software. By creating a distinct type, you can prevent a whole class of logical errors. It's like having a key that only fits one specific lock. Plus, you can attach methods to your new type. This means you can take something as simple as an integer, give it a new type name, like customer ID, and then add methods to it, like asValid. And this example just shows the benefit perfectly. Imagine you have a product ID and a customer ID. And under the hood, they're both just ints. It would be so easy to accidentally pass a product ID into a function that's expecting a customer ID, right? That could be a disaster. But with defined types, the compiler just stops you. It gives you an error. That bug becomes literally impossible to write. It's an amazing safety net.
Understanding this difference isn't just about syntax. It's about making smart architectural decisions. This is one of those fundamental Go concepts that separates a junior developer from a senior one. And I'll let you in on a little secret. This comes up in senior engineering interviews all the time.
So let's put it all together with a question you are very, very likely to see in a Go interview. Ready? This question gets right to the heart of it. It tests if you really get Go's type system and know how to choose the right tool for the job.
And here it is, the crisp, complete, perfect answer. Type A is B is a type alias. A is just another name for B. Type AB is a type definition. It creates a brand new, distinct type. If you remember that an alias is for refactoring and a definition is for safety and adding behavior, you've got it.
Okay, we've covered a ton of ground, so let's do a quick recap of the whole Go type toolkit. We'll lay it all out side by side. This is probably the part you want to take a screenshot of.
First, here are the tools for changing and revealing types. Notice the clear progression here, right? Conversion is compile time safe. Assertion is runtime safe as long as you use the "OK" idiom, and casting is just plain unsafe. The takeaway is simple. Always reach for the safest tool that gets the job done. And here's our summary for naming types. This table makes the trade-off crystal clear. A type alias gives you convenience, perfect for refactoring. A defined type gives you compile time safety and the power to add new behavior with methods. That's what you want for building robust, self-documenting code.
So what's the big takeaway from all this? Is that Go's type system isn't there to be a pain. It's a guide rail. It's designed to help you write better, safer code by forcing you to be clear and intentional. It pushes you to think through your data, and in return, the compiler becomes your best friend in catching bugs. So my advice? Embrace the strictness. It's there to help you.